Good evening, everyone. Welcome back to the Linear Algebra series. This is sort of episode 3 in the series on matrices and matrix algebra. Okay, so we've sort of finished the first chapter of the course, which was all about linear systems, and now we're moving on to matrices, and then we'll come back to linear systems in sort of the third section as well. I will from now on be assuming that you have that knowledge, so if you don't, go check out the videos. They're, don't know why I'm pointing upwards, but they're on my channel, you can check them out. And the second one, there's a bit of an audio issue. Hopefully that doesn't happen for this as well, but hopefully that will resolve for this video, I'm hoping, because otherwise I'm going to have to re-record this. But hopefully it's still watchable, so I decided not to re-record it because I thought it was still watchable. So let's just move straight on to matrices and matrix algebra. So I guess what really is a matrix? A matrix is just a two-dimensional array of numbers, right? At its simplest, right? And by two-dimensional we mean it's really just governed by rows and columns, right? There's nothing else, right? If it was three-dimensional, maybe there'd be something coming out the page and like some numbers stored sort of not only along rows and columns, but maybe along some sort of height thing. But in this case, it's two-dimensional because we only care about rows and columns in terms of describing our matrices, and I'll talk about that as well. Effectively, a matrix is just a two-dimensional array of numbers. So it's just something that we can store our numbers in that has rows and columns, which is what we mean by two-dimensional. So I guess, for an example, so e.g., so I shouldn't really put those dots there, sorry. So e.g., we could have something like this. So we could have 1, the square root of 2, 2, pi, minus 3, 0, that's a matrix, right? Literally, again, we have some rows, we have some columns, and we have some numbers inside those rows and columns, and that's pretty much all a matrix is. At least at its simplest, right? This is sort of the easiest explanation I could give you as to what a matrix is literally just this, a two-dimensional array of numbers, so some rows, some columns, and some numbers inside. That's all we mean. I guess we could also have, there are other examples, right, of matrices you could have. So for example, maybe something like this. You might be familiar if you've done A-level seeing something like this to represent a column vector. We'll talk about those as well. And also you might think of a matrix as something like this. So in this case, our matrix has all zeros inside. And that's fine, right? We never specified which numbers have to be inside, just that it's two-dimensional. So it has some rows and it has some columns. Okay, very nice. So these are all matrices. And this matrix here, this is a 2 by 3 matrix. So what that means is we have 2 rows and 3 columns. And so you would obviously also expect this here to be a 3 by 1 matrix, and this one over here to be a 2 by 2 matrix. Okay. And so yeah, so the first number here, whenever we have that sort of AXB, so A by B matrix, actually I'll write this somewhere else. So whenever we have an A by B matrix, what we really have is A horizontal rows. So A just tells us how many horizontal rows our matrix will have, and B vertical columns, right? So, and we know that should give us enough information to describe our matrix, because matrices are just two-dimensional arrays, right? So they must only have rows and columns. There's not going to be something else. And so we can basically describe what our matrix might look like without actually putting any numbers inside it by this sort of A by B figure here, and that's what we typically do. To talk about, I guess, what size our matrix is. Okay, let's talk a little bit about row vectors and column vectors. So row vectors in Rn are effectively just 1 by n matrices. So you can think of row vectors as matrices that have one horizontal row and n vertical columns, so something like this. And these were exactly the kind of things that described our solutions to our linear systems. We call these row vectors. That's pretty much it. We also have column vectors in R col n are n by 1 matrices. So we have row vectors are, I guess, technically can be defined as 1 by n matrices, if we're happy with that definition of a matrix, which you might not be, but we're going to take it for now. And then column vectors are going to be n by 1 matrices. Okay. I guess by definition, we can, so with all this information, we can say that we have m and n as positive integers, so that could be 1, 2, 3, 4, 5, 6, so on and so forth, just like natural numbers. Be positive integers. And m by n matrix is an array of real numbers, is an array of real numbers arranged into m rows and n columns. So this is just a guess, since we've had that discussion about what it means to be an m by n matrix, what it means to be a matrix, then we can combine those things into one definition, which tells us that if we have m and n as positive integers, so just like natural numbers, so 1, 2, 3, 4, 5, so on and so forth, then an m by n matrix is an array of real numbers arranged into m rows and n columns. That basically summarizes everything I've spoken about. Okay, very, very nice stuff. Okay, so if we look at some of the matrices that I sort of displayed earlier on, and we try and sort of identify the rows and columns, then we can see that if I give you, so if I have, so as an example, if my matrix M, this is going to be that first one from the example before, which was 1, the square root of 2, 2 pi minus 3, 0, right? If that's true, then the second row of M is going to be sort of the square root of 2 pi 0, right? So it's just going to be like that row vector, that 1 by 3 row vector with the elements root 2, pi, and 0 inside it. That makes sense because we're literally looking at a row, so that should just give us a row vector, right? So literally isolating that row. Okay, and we also have, so then the second row is that, and the third column, and the third column is minus 3, 0, right? And this is going to be a 2 by 1 column vector, which makes sense again because we're isolating now the columns, and it's giving us this thing over here, this minus 3, 0. Okay. Very nice, and that makes sense, right? Because we're just counting in order here. So that's the first column, that's the second column, that's the third column. Okay. should be so self-explanatory so far. Okay, so let's also have write a definition here about what actually are these numbers in our matrix. So, well, the numbers in a matrix are typically referred to, and we'll define them to be, its entries. So the entries of a matrix are just the numbers inside it. So that's effectively what's going on. So if I give you, so given an m by n matrix, call it capital A, we will write lowercase a ij for the entry in the ith row, sorry, give me a second here, and the jth column, right, and that will definitely give us a unique entry, because again, our matrices are basically just two-dimensional arrays, right? They're just going to have rows and columns, so each element, each entry within our matrix is going to be allocated to some row and some column, right? And that's going to be unique, right? So, for example, if I give you the matrix A is equal to 1, 2, 2, 1, then this element up here is associated to the first row and the first column, but this element down here is associated to the second row and the first column. And so, because these matrices are two-dimensional, there's nothing else we need to specify. To locate, to pinpoint a unique element, we only need to specify the row that it's in and the column that it's in. Simple as that. And so we can denote these entries as aij, where I is the row of the entry and j is the column. Okay, so I think, yes, the final important piece of detail is that I can vary between 1 and m, because remember, we have an m by n matrix in total, which means we must have m rows in total. So our possible choices for I are going to be 1 for our first row, 2 for our second row, all the way down to m. So we will technically just have 1 less than or equal to I, less than or equal to m, right? Similarly, j can vary between 1 and n, right? So 1 is going to be less than or equal to j, is going to be less than or equal to n. And the reason for this is just very simply because we will have n columns, and j is dictating which column our entry is in. And so we can pick the first column, the second column, all the way up to the nth. But there is no n plus 1th column because we have an m by n matrix in total. Okay, so that's the definition there. So what we have is that the ith row is going to be given by ai1 all the way up to ain, and sorry, I should move this down, and the jth column is given by a1j all the way down to amj, right? Because we have m rows, right? So this is sort of on the mth row, whereas this element here is on the nth column, right? Even though we're talking about a row vector, we are still denoting the column of the element with this second subscript. So with that n, that's denoting what column our entry is in on this specific row. And this m is denoting which row our column is in, which row our entry is in on this specific column. Okay, perfect. So we can keep moving forward. So I guess we shall, just as a piece of notation, we shall denote the set, so the set of real m by n matrices. So all the possible m by n matrices you could ever dream of, we're going to put them all into one big set. It's going to be lots of them, right? Infinitely many. but we can still chuck that all into a set as long as there's no contradictions with that set and its existence, which in this case there wouldn't be. So we shall denote the set of all real m by n matrices as m, capital M, followed by lowercase m, lowercase n, right? And so what we can do with this is we can note a couple things about this. Well, we know, so note that the set of all 1 by n matrices is just our row vectors Rn. So Rn is just the set of all row vectors, basically, with n entries, okay? Because we always know that it will be 1 by n, so we need to choose what our n is. The 1 is locked in, but we need to choose what our n is. So that's what the n here is representing the choice of entries in our row vector. But it's effectively just saying the set of all row vectors with n entries. So we have that, but also the set of all matrices, of all n by 1 matrices, well, that's just going to be our column vectors. So this is just representing the set of all column vectors with n entries. So the same idea as the row vectors, just we put col here to make sure that, to distinguish between row vectors and column vectors. Okay, so there are some important operations we need to be able to perform with matrices. We need to be able to add matrices, multiply a matrix by a scalar, and multiply two matrices. And we need to be quite careful about how we define these things. We want to define these things properly. Okay. And very similarly to how you might have seen things work with vectors, if I give you two matrices, it's not always true that we can add them together, and it's certainly not always true that we can multiply them. Okay, so you need to be careful about how you're defining matrices, and then once we're careful about that, we need to be careful when we're multiplying them and making sure that we're abiding those rules, because those rules aren't going to hold for all pairs of matrices that I can give you. Okay, they're going to hold for a specific subset, which we'll talk about in our definition. Alright, so let's talk about addition of matrices. So definition. So we have here we have the addition of matrices. So addition. So we're going to say let capital A equals, so we're just going to denote sort of it as this sort of brackets Aij. And so effectively we're just using shorthand there and saying that effectively this is going to be an m by n matrix, so m rows and n columns. Sorry, I'm just saying matrix. So this is just some shorthand here. We're saying capital A is a matrix, and I guess we're going to talk about the entries within that matrix as all our Aij's. So this is just saying that the entries of our matrix are represented by Aij, where I is that ith row and j is that jth column. It's just the shorthand that we're using because for our definition, you don't want to write out our matrices, and we want to be as general as possible at the same time. So that's just a nice way of doing it. Okay, and we're going to have to also let capital B equals Bij, so that's another matrix, be a P by Q matrix. So P rows and Q columns, right? To add A and B, so to add A and B, it turns out that we must have M equals P and N equals Q. So one way of thinking about this is that we need to have our matrices being the same size to add them together. So that's what I meant, right? We can't just take any two matrices and add them together. With this definition, we need to make sure they have the same size. So if I give you an M by N matrix and a P by Q matrix, I can only add those two matrices if M equals P and N equals Q. So I can add a 2 by 3 matrix to a 2 by 3 matrix, right? I can add a 1 by 1 matrix to a 1 by 1 matrix. That's fine, perfectly fine. But we cannot add a 2 by 3 matrix to a 2 by 4 matrix. Not doable, okay? So I guess we can then follow that up by saying if we write capital C So this is capital C will be another matrix, but we're going to define that matrix to be the sum of capital A and capital B, given that we're allowed to do that. And we'll just use the shorthand here, so Cij, so the entries of that matrix C will be represented by Cij. Then what we'll have is that Cij is going to be equal to Aij plus Bij, right? So that will be true for 1 less than or equal to I less than or equal to M, and also for 1 less than or equal to J less than or equal to M. So this should just make intuitive sense, right? Effectively, to add two matrices, you're going to add together their corresponding components, right? I guess we can have a look at an example. So effectively, if I wanted to add, so if I wanted to say what is sort of my sort of entry of C in the first row and second column going to be, that's just going to be my entry of A in the first row and second column, plus the entry of B in the first row and second column, right? So it could be something like this: 1, 1, 1, 1, plus 2, 2, 2, 2, right? These are two matrices, they have the same size, they're both 2 by 2, so we can add them, that's good. Now we want to find C12. So C is going to be another matrix that we get from this, right? Well, C12 is just going to be A12, so that's just going to be my entry in my first row, second column, so that's a 1. And then B12, so first row, second column, that's a 2. So then I'm going to get the entry in my first row and second column here is going to be a 1 plus 2 is going to be a 3. And you do this for all the other entries and you get this as your resulting matrix. You can just basically add together those components pairwise as you would expect. So that's quite a nice way of doing things. And of course we can only, I cannot be bigger than M because it's literally M, our matrices A and B are M by N. So it must mean we have M rows and, sorry, actually I meant 1 less than or equal to J less than or equal to N. Not M, sorry, I think that was a bad N. So we have M rows, which means that our I is restricted by M, and we have J columns, which means our J is restricted by N. Sorry, and we have N columns, which mean our J is restricted by N. So our I is restricted by M, and our J is restricted by N, because we have M rows and N columns. And so our I we could be picking an entry in the first row all the way up to the nth. We could be picking an entry in the first column all the way down to the nth. Okay, so let's have a look at an example, I guess. So this is very intuitive, right? Or at least I hope it feels intuitive. It will definitely feel intuitive relative to matrix multiplication. But let's have a look at an example here. So an example is we have that, so we're going to say let the matrix A be equal to 1 minus 1 to 0. I'm also going to say let C equal 1, 1, minus 1, minus 1. Right. So the matrix A plus the matrix C, and first of all we need to check they're the same size. So this is a 2 by 2, so that's good. And this is a 2 by 2, so we can add these two matrices, that's good. And then we need to add their components, so we're going to add them one by one. So 1 plus 1 is 2, 2 plus minus 1 is 1, minus 1 plus 1 is 0, and 0 plus minus 1 is minus 1, right? Also, we also have that the matrix C plus the matrix A is going to be 1 plus 1 is 2, minus 1 plus 2 is 1, 1 plus minus 1 is 0, and minus 1 plus 0 is minus 1, right? So we notice that C plus A is actually going to be equal to A plus C. So clearly C plus A, the matrix C plus the matrix A, is equal to the matrix A plus the matrix C. Then the question we have is this true in general? Is this true in general? And perhaps you might wonder why. So whenever I have a matrix A and a matrix C, as long as I can add them, is it true that you can add the matrix C and first and then the matrix A, and that will give you the same thing as if I do the matrix A first and add that to the matrix C? And the answer is yes, it is indeed true. By the way we defined it, right? The reason why is because we defined it that way, but specifically because we're adding those entries. Those entries are just real numbers, and real numbers have a property called commutativity of addition, which means that if any two real numbers I give you, I call them A and B, A plus B is equal to B plus A. And so really I'm just adding these real numbers. Well, for now they've been real numbers, and I'll just assume they'll be real numbers, but we won't get into complex numbers. So I'm just adding these two real numbers, right? And so I can do that in any way I want, and it still gives me the same result because of the commutativity of addition, right? And why is addition of the real numbers commutative? Well, we can go to real analysis and have a discussion about that later. But for now, that's the reason that you should have in your head as to why this is true. And so we know that in general, matrix addition is commutative. Addition is commutative, right? And what this means is for matrices M and N, so for matrices M and N of the same size, we have the matrix M plus the matrix N will always be the same as me adding the matrix N to the matrix M the other way around, right? So the addition of matrices is commutative. It's a commutative operation, which means I can do it in any order I want and get the same result, right? So hopefully that makes sense. Now we also know that the addition of matrices is going to be associative. So we know that when we add two matrices, that's going to be an associative operation. So what does that mean? Some of you might know what that means, but if you don't worry. Associative, right? So what that means is that basically if I gave you three matrices, call them L, M, and N, then L plus, in brackets, M plus N, right? So if I do L first, then I figure out what M plus N is, and I add that to L. I should get the same result as if I do L plus M first, I find what N is, and I add that to L plus M. So effectively that's what associativity tells me. It tells me that I can move these brackets around as sort of any way I want to, so they could be around the M plus N, or they could be around the L plus M if I wanted them to be, and the addition of my matrices still gives the same result. So I can add M plus N first, and then add that to L, and I get the same thing as if I added L plus M first and added that to N, and that's perfectly permissible. And again, the reason for that is because, well, we're just adding real numbers, and when we add real numbers, that is also associative. Well, why is that? Then you can have a look at some of the field axioms in the beginning of the real analysis course, which I might talk about at some point in time on this channel. And obviously we have this only for matrices of the same size, right? Because you can't add two matrices that don't have the same size for matrices of the same size. Okay. Okay. So now let's talk about something else before we move on to scalar multiplication. So let's define the zero matrix. So definition. The M by N zero matrix is the matrix with M rows and N columns, is the sort of matrix with M rows and N columns such that all of its entries are going to be 0, such that all its entries are 0. Okay, so the matrix, so we actually denote the matrix. So the matrix is denoted as just sort of 0, like that, unless we need to specify its size. So unless we need to specify the size of the matrix, to specify its size, in which case we denote the matrix as 0 with a subscript mn to indicate how many rows we have and how many columns we have. So m is our number of rows and n is the number of columns, okay? As you would normally expect. So as an example, so for example, the 0 matrix with the 2, 3 subscript is going to be a 2 by 3 matrix. So 2 rows and 3 columns, and all of the entries will be zeros. A nice fact that you should accept and see is that for any matrix A, so for an m by n matrix A, then we have A plus 0 mn, so that matrix plus the 0 matrix of the same size is always going to just give me my matrix A back. And by the commutativity of matrix addition, that's the same thing as me doing the m by n 0 matrix plus A. So obviously for any m by n matrix A. And well, why is this? Well, because we're literally just adding 0 to every single component. And again, this comes back to the field axioms, which we'll talk about in real analysis if you're interested, which will be something I talk about later on the channel. Effectively, any real number plus 0 just gives you that real number back. That is an axiom or an assumption that we make, and it's very crucial here to seeing that any matrix plus the 0 matrix of the same size just gives you that matrix right back. Okay, just don't want to make this video too long. It's probably going to be around 30 minutes at the moment, so we can go for another 10-15 minutes. Let's talk about scalar multiplication then. Okay, scalar multiplication. Scalar multiplication. Perfect. Right, let me just move this down. Okay, so again, we're going to be formal here. Well, slightly formal. We're not going to write out the matrix, but we will say let A, which we're going to write in this form, Aij, like so. That's just a shorthand to represent a matrix with entries given by Aij, where I is the row of that entry and j is the column of that entry. So we're letting that be a matrix. Specifically, it's going to be an m by n matrix. And we're going to take k, and we're going to let k be a real number. And if we have a real number, we also sometimes call those things scalars. So in this case, those two things are basically the same. Our real number k is a scalar as well. It just means, again, those you can use those words kind of interchangeably. K being a real number means it's a scalar. So k is our scalar, k is a real number, those are the same thing. So then we have a matrix and a real number, and we're going to define a new matrix. Then the matrix Ka is defined to be the m by n matrix. So that's still going to be an m by n matrix. So we multiplied it, we've made a new matrix, which is still going to have the same size, m by n matrix, with the sort of ijth entry equal to k times aij. So you take every single entry of the initial matrix and you multiply each entry by the real number k that we've effectively just put in front of our matrix. So if we want our matrix K capital A, then we just take each entry of our matrix A and we just multiply it by K, where K is just some scalar or a real number. Simple as that. Okay, so if I have, so I guess we should also have a look at an example here. So here's an example. So if I have a matrix A, which is given by 1, 2, 3, 4, and we have a matrix B, which is given by 0, -2, 5, 1, then we are asked here to show that 2 times the matrix A plus the matrix B is equal to 2 times the matrix A add 2 times the matrix B. So first things first, we can calculate the matrix A plus the matrix B from before. That gives us 1 plus 0, so that's going to be 1. 2 plus -2 gives you 0. 3 plus 5 gives you 8. And 4 plus 1 gives you 5. And so that means that 2 times A plus B is just going to be equal to, so this is now using the new thing we've just defined, that scalar multiplication, so we can multiply each entry by 2. So 1 multiplied by 2 is 2, 0 multiplied by 2 is 0, 8 multiplied by 2 is 16, and 5 multiplied by 2 is 10. Okay, then we know what 2 times A plus B is. Now we calculate 2A, so this is again just using the definition of scalar multiplication here. So we know what A is, so we multiply each of the entries in A by 2. So 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and 4 times 2 is 8. And we also have that 2B, 2 times the matrix B is just going to be 2 times all of its entries, so we get 0, -4, 10, and 2. So if we add those two things together, so we get 2A plus 2B is equal to, so 2 plus 0 is 2, 4 plus -4 is 0, 6 plus 10 is 16, and 8 plus 2 is 10. And notice that this is actually the exact same as 2 times the matrix A plus B in brackets. And so we are now going to be checking, so effectively we've just now proven a specific case of what we like to call the distributive law. So in sort of typical algebra that you might be familiar with from high school, from secondary school, you might know, sorry, let me just extend these boundaries here, give me 2 seconds. You might know some rules about how we can distribute things, and so you might know how to distribute sort of multiplication over addition, or is that right? How to distribute sort of a scalar, so how to distribute a scalar. Sorry, I don't know how to say this properly. I'm sorry. You don't distribute multiplication over addition, but you see what I mean. That effectively, I hope you understand what I mean. That effectively, you should be familiar with in algebra, me multiplying 4 by something like 2 plus x. So to do this, you multiply 4 by 2, and then you multiply your 4 by x. So this is actually the distributive law in action, but with real numbers. Well, assuming x is a real number, which is fine. And this again, it all comes back to the field axioms which we'll talk about in real analysis. But effectively, you should be familiar with doing something like this in high school or secondary school, so distributing the scalar over this sort of sum of two terms. And that gives you 8 plus 4x. And I guess the question is that always true if instead of real numbers, these two things are matrices? Well, yes it is, because remember, we've just defined everything to do with matrices in terms of its entries, and those entries are pretty much defined to be real numbers. So everything that works for real numbers is so far also going to work for matrices. So we can distribute matrices over, so we can distribute the sort of the product of a scalar by the sum of two matrices exactly as we would with real numbers, really. So that's what we can take from it. So that's called the distributive law. So I guess that there is called the distributive law. Okay. So I guess we've had a discussion about commutativity, associativity, distributive law, that sort of rule with the zero matrix. So how can we combine all these rules to give us, well, how can we combine all these rules really is a question. And there is a way to do that. Well, you could do it arbitrarily, right? But as mathematicians, we want to have a sort of coherent list of basic rules, which we can sometimes take to be axioms. In this case, because we've been defining things and literally building up what matrices are, we are just taking them to be sort of cool consequences of the way that we've defined things, right? Which they technically are in this case. But sometimes we want these things to be axioms, so we can talk about more general structures in maths. And so what we want as mathematicians, we want to have a coherent list of very simple rules which we can take to be axioms when talking about some types of mathematical structures. And in this case, the type of structure which we will want to talk about is called a vector space, specifically a real vector space. And the list of axioms go as follows. So, sort of, I guess this is a remark. In general, the following identities hold. In general, the following identities hold. So I'm first going to say let A, B, and C all be n by n matrices, and let lambda and mu be some real numbers, which is why I said a real vector space. So there's a hint, because we're dealing with lambda and mu being real numbers. So that concept of real numbers is coming into things here. And so we have these rules. So the matrix A plus the zero matrix of the same size is going to be equal to the matrix A. We also have the matrix A plus the matrix B is equal to the matrix B plus the matrix A. So I have 0, so the zero matrix, right, multiplied, well, sorry, not the zero matrix, just 0 as a scalar, multiplied by matrix A is going to give me the zero matrix of the same size as A, right, because I'm multiplying each element in A by 0, right, and A is n by n, is an n by n matrix, so the result will be a n by n 0 matrix, since anything times 0 gives you 0, and that's again another field axiom there. So there's a really big tie here between the field axioms, if you're familiar with those, but basically just the assumptions we make about how the real numbers are behaving under addition and multiplication, and these basic matrix laws. Okay, and we also have that the matrix A plus the matrix minus A, which is going to be the matrix multiplied, everything in the matrix multiplied by minus 1, is going to give us the zero matrix of the same size as A. And again, that's because that's linking back to real numbers, because every entry in A is going to be a real number, but every entry in minus A is going to be the same as every entry in A, but just with a minus in front, right? Or you remove the minus if the entries in A were all negative or whatever, but you see what I'm saying. And so that means that every entry in A, which can be a real number, add minus that real number, gives you 0, right? 2 plus minus 2 gives you 0, minus 4 plus 4 gives you 0, and that just, again, that comes back to an axiom to do with how the real numbers are behaving under addition and multiplication, precisely because we've defined the addition of matrices to be the addition of the components in those matrices, and those components are just real numbers. So that's why we get this. We also noticed before the associativity of matrix multiplication, so the matrix A plus B added to the matrix C is the same as me adding the matrix A to the matrix B plus C, and we also have 1 multiplied by the matrix A gives me the matrix A, so that's another rule, which is pretty obvious, right? If I just multiply every entry in A by 1, I just get the same matrix. And then we also have the this is the distributive law. Well, actually no. So this is another form of the distributive law, which effectively says that if I have two real numbers, lambda and mu, then lambda plus mu multiplied by my matrix A is going to be the same thing as me multiplying my matrix A by lambda, and then adding that to my matrix A multiplied by mu. And the reason for that is because, well, this is just a real number, right? And so every single entry in my matrix is going to be a real number, and every single entry in my matrix will be scaled up by lambda plus mu, and any real number times lambda plus mu is that real number times lambda add that real number times mu. And again, it's coming right back to the axioms for the real numbers, right? So there is a big link in here. And then we also have another form of the distributive law, which is one that we saw in the previous sort of example. So any real number lambda multiplied by the sum of two matrices is just going to give you lambda times the first matrix plus lambda times the second matrix, right? So we're adding those two matrices up, right? And then effectively we are going to be multiplying that result by multiplying every entry in that new matrix by lambda, and that will be the same as if I just took each individual matrix and multiplied the entries by lambda and then added them together, and that's again coming back straight to the real numbers again. The final rule we have is that lambda times mu A is going to be the same as lambda mu times A. So it's another form of associativity, but specifically in this case, effectively scaling up every entry in a matrix by mu and then scaling up by lambda is the same as just scaling everything up all at once by the product mu lambda. And that makes sense, right? Because if I multiply a real number by mu and then by lambda, it's the same as if I multiply a real number by mu then lambda. So that there is, again, coming straight back to how the real numbers are working, because every entry in the matrix is just a real number. We have basically just been defining everything in terms of how the entries of matrices are interacting. So these rules just basically come straight from that. And so we say that these rules, that these identities make the set of all m by n matrices, the set of all m by n matrices, a real vector space. So let me just talk about that and then we can finish up for today. So space, so, oh my goodness, it's not letting me write this properly, a real vector space. So the reason why I've said real vector space is because mu and lambda are real numbers. So that's really where that's coming from. And a vector space is just a type of mathematical structure which is governed by these rules that I've stated over here. And sometimes we take those rules to be axioms. In this case, we just take them to be identities that come from the definitions that we've introduced. But if we're being very general, we like those to be axioms because we can't quite prove them in general for all types of structures. In this case, for the structure that is the set of all m by n matrices, we can if we define things in a certain way, but it often helps us to be as general as possible, and that means we can basically collect all of these structures into sort of one big sort of thing and prove things about that big thing. It's slightly vague, But effectively, instead of taking specific cases, we can put all cases into one and then prove everything for that big case, as opposed to proving everything for the small cases. And that's what we do. But in this case, we've just taken a small case because we want to show it an example of what a vector space is, and then later on we can sort of generalize that to all types of vector spaces and take these to be the vector space axioms. And with that, I finish for today. Next time we'll talk about matrix multiplication, and we'll also talk about the identity matrix, the Kronecker delta, the sifting property of the Kronecker delta, some properties of matrix multiplication, and maybe some invertibility stuff. So I'll see you then. Goodbye.